Hi guys, today we're going to look at chromatography, which is covered in both C1 and C8. So it's part of the separating mixtures part where you look at different separation processes such as distillation, filtration, crystallization, and also in the chemical analysis topic. So in a mixture, you've got separate substances and they're not joined together with chemical bonds. So, for example, you have got some jelly beans and you just want the red ones out. You can easily separate the different parts of the mixture using physical processes. Because they are physical processes and they are not joined by chemical bonds, there's no chemical reactions involved and no new substances are made. So typical examples that we talk about in chemistry include air. So we know in air we have the oxygen, carbon dioxide, nitrogen, small amounts of argon. Those different elements and compounds are all existing, but they're not actually joined together with a chemical bond. Another example is steel. We say it's a mixture because different steels from different companies, for example, might have different amounts of iron in there or zinc or other types of metal. So what we're going to look at is paper chromatography. And we use paper chromatography to separate mixtures of soluble substances. And we could be looking at food colorings, inks, dyes, plant pigments. And we would have looked at something more than likely felt tip pens when we've done this required practical earlier on in school. So you might recognize something that's on your screen. You would have done it probably with a small strip of paper, and you would have had a splint at the top holding the paper up, attached with a little paper clip. You can see in the picture that there's 5 little bottles. So on that chromatography investigation, you can see there's 5 rows of colours, and you've been able to see how the colours have separated out. Part of this topic, chromatography, you might actually be asked to explain a method, plan an investigation into an unknown dissolved substance. So if your little piece of filter paper, and you would have drawn a horizontal line about 1 centimetre from the bottom in pencil. We use pencil because it is insoluble and will not dissolve in the solvent. You would then take your unknown substance, like I said, we might have done felt tip pens, and you put a little dot in the middle of the line. When you're trying to identify what is in an unknown substance, say for example this black felt tip pen, you have to have known samples to actually compare it to. So we call these our reference spots. At the end, we will be able to compare how far our unknown substance has rose along with the known spots. So here we've got our filter paper with our pencil line and our dots, and we would have put it in a solvent. What solvent we would have used would depend on what we are actually trying to investigate. So, for example, if I was going to look at waterproof pens, I would not use water as the solvent because the water would not be able to carry the ink as it is insoluble. So, for example, if I wanted to look at waterproof pens, I might use ethanol as the solvent instead. When you did your practical, you would have had your pencil line and you would have made sure that the pencil line was always above the solvent. That's because otherwise, our substances, if they were underneath the solvent, they would become washed away and we wouldn't be able to see anything. So that's one really, really important thing to be aware of, and they generally look out for it. So in paper chromatography, the solvent rises up the paper and it takes the dyes with it. Different dyes travel at different rates in different solvents. Let's say I was looking at a particular food additive and I put it on my baseline and I try it with one particular solvent. I then also do another solvent with the same food additive. Different dyes will move at different rates with different solvents. So let's say I used it with solvent 1 and it only rose about 4 centimeters, but solvent 2, different one completely, the same dye, the same food additive might actually rise 6 centimeters up the paper. So different substances travel different distances with different solvents. We might actually see on our chromatography that 2 dots have rose to exactly the same spot, so it looks like we've only got 1 dot. This is where we'd use different solvents to then separate them out so that we could see exactly which chemical we have in our unknown substance. So when we have set up our experiment, we've got our pencil line, we've got our dots, and we are waiting for the solvent to rise up the filter paper, we would have taken it out when it gets close to the top. So at the end of the day, we actually want to measure how far the dyes have moved and the solvents moved. So we'll take it out and we would draw a pencil line near the top to where the solvent reached. And we call that line a solvent front. Again, we've got to do it in pencil because pencil is insoluble. So the solvent has carried the dyes up through the paper. If our dye, our original dye, has stayed on the baseline, we say is insoluble. Whichever colour, dye, substance has moved the furthest up the paper, we say that is the most soluble. And anything that's lower, hasn't really travelled very far, we say that is the least soluble. So if it's stayed on the line, it's insoluble. If it's travelled the most up the paper, it's the most soluble. And if it's pretty low down, we say it's the least soluble. So we have set up our method, we've waited, we've taken the paper out when it's got towards the top. What we end up with is something called a chromatogram. So your original substance has separated out into different spots. Each spot that you can see on a chromatogram is a different substance. So this one on our screen contains 3 different substances. 3 spots, 3 substances. Like I said, sometimes you get 2 dots that have travelled the same distance. To separate them out, you would have to use different solvents, as they would then travel different distances. If you only ever get 1 spot, it means it's a pure substance. So in chromatography, we talk about phases. And you might remember a mobile phase and a stationary phase. So the mobile phase is a solvent. It's moving through the paper, carrying the dissolved substances. In chromatography practicals investigations, it could actually be a liquid or a gas as our mobile phase. When we've done it in class, we've just used a solvent and that has been our mobile phase, and it's a liquid. Stationary phase in paper chromatography is the paper. And this is where the mobile phase moves through it. Stationary, it cannot move. The molecules cannot move. In other types of chromatography, you might actually have a really thick liquid as the stationary phase. Paper chromatography, it's the paper. So different substances have different attractions to the mobile phase and the stationary phase. They're attracted to them both in different proportions. So say something was very attracted to the mobile phase, it would move quite far up and it will move quickly with the mobile phase. If it was attracted to the stationary phase, it would not move very far up the paper. So it all depends on how attracted they are to either the mobile phase or the stationary phase. So if it's really attracted to the mobile phase, it moves quickly up the paper. If it's attracted to the stationary phase, it doesn't really move very much. So how can we interpret a chromatogram? So this is what you would probably see in an exam question. And there's several things we can get from this picture. You might actually be asked to measure things, which we're going to go through later on. So on this screen here, I've got my start line at the bottom, I've got my solvent front at the top where the solvent got to, and I've got on the right hand side my original unknown substance, which was black ink. And you can see there it's separated out into two spots. On the left hand side, you can see my sample reference spots. I've got blue ink, I've got red ink, and I've got yellow ink. So the first thing that I would look at here is what spots are in my black ink. So this is where you have to compare the distances that they've moved up the paper. So you can see here, I've got two dots in line with each other. I've got a red ink, and it's in line with the spots on the black ink. So that tells us that that black ink could most likely have that red ink in its components. We can also see that there's a spot in the blue ink, which is in line with one of the spots in the black ink. That could again tell us that that black ink contains the blue ink. There's no spot in line with the yellow ink, so that yellow is not in that black ink. Let's say I actually had a third spot on the black ink and it wasn't in line with any of the samples. When asked to interpret a chromatogram, we would actually have to say it contains a blue ink, a red ink, and an unknown ink. If we don't know what it is, we have to say it's an unknown ink. Like I said, you might actually have to measure spots. So you'd have to say what's in line, and then you actually have to do something called an RF value, where you have to actually calculate. And this RF value is a retention factor. And it's a ratio between the distance travelled by the substance and the distance travelled by the solvent. Because it is a ratio, there is no units. So you might be asked to measure and calculate this RF value, and we're going to have a go at it in a minute. Because it's a ratio, there are no units, but you might need to measure in millimeters. There actually might be a question that tells you to measure in millimeters. It might tell you to measure in centimeters. So when you read these questions, be very careful and make sure you know what it's asking you to measure it in. So that's usually a mark. So let's say we're going to look at the red ink. We know that the black ink has red ink. So when you measure, and you will literally do this with a ruler, you have to measure to the middle of the spot. Not the bottom, not the top, in the middle of the spot. And you'll always start at the start line from where it travelled to. So we've got our distance travelled by the substance. Like I say, it's in the middle. Then we have to look at the distance travelled by the solvent. We start and we measure the difference between the start line and the solvent front. That is your distance travelled by the solvent. The difference between the start line and the solvent front. So let's have a look at this. So we could say that the red ink moved 13 millimeters and the solvent travelled 43 millimetres up the paper. So if we use that calculation, RF value equals distance travelled by the substance divided by distance travelled by the solvent. We would plug those numbers in, so we'd have 13 over 43, and we'd come out with an answer of 0.30. It is a ratio, so there's no units, and your answer should always be below 1. Because of the way the equation is, your distance travelled by the substance will always be smaller than the distance travelled by the solvent. So you're always going to have your small number above the bigger number. So your value should always be below 1. If it's not, recheck which way you put your numbers in your calculator. So your first task is to look at this picture, and it says the figure above shows a paper chromatogram of 5 different inks. The blue ink has moved 1.3 centimetres and the solvent has moved 5.3 centimetres. Calculate the RF value for the blue ink. Pause the video, have a go at this calculation, and then move on. Task 2. A student used paper chromatography to identify the colours in a black ink. The diagram above shows the student's results. The green colour travelled a distance of 13 millimetres and the solvent travelled a distance of 36 millimetres. Calculate the RF value of the green colour. Again, pause the video, have a go at this problem. Make sure you are writing down your calculations. You tend to get marks for actually writing down your calculations in pretty much most of any equations you're going to use in science. So always write down your calculations. Task 3. Chromatography was used to compare 3 of the colours used to coat chocolate sweets. Colour 2 travelled a distance of 48 millimetres and the solvent travelled a distance of 58 millimetres. Calculate the RF value of colour 2. Pause the video, have a go. Task 4. The chromatogram shows the results from a horse's urine sample. We've got a key down the side. So number 1, caffeine, 2, cocaine, 3, ketamine, and 4 is the actual urine sample that was taken. So you've got 2 parts to this question. A, which of the 3 substances, caffeine, cocaine, and ketamine, is the least soluble? And B, which substances does the urine sample contain? If you're not too sure how to answer this question, go back and listen to my voice again, where I've told you how you can find out which one is the least soluble, the most soluble, or insoluble, and how to interpret a chromatogram. I did the example with the black ink near the start. Final task, task 5, is to answer the following questions. Number 1, what does the start line need to be drawn in? Number 2, where must the solvent be in comparison to the start line? Number 3, what must be added to the start line if you want to know what substances are in an unknown mixture? Number 4, in figure 1, top right, how many colours are in the food? Number 5, in figure 2, which additive has been added to the orange drink? Pause the video, have a go at these questions. Send your answers to your member of staff. If you're listening to me and it's my work, send them to me. And thank you very much for listening.